Welcome. This video is going to look at the second part of 4.1, looking more specifically at ionic structure and the properties that results in for ionic compounds. So the structure of an ionic compound is very three-dimensional. It's this lattice, so think of it as a three-dimensional ladder of alternating cations and anions, and it's called an ionic lattice or a crystal lattice. So they have a very crystalline structure, and the geometry is going to depend mostly on the size of the ions, but also on the ratio of ions, if it's 1 to 1 or 2 to 1. So think of your 8th grade rock and mineral units where you cleaved it and it was hexagonal or cuboidal or whatever. That's the crystal lattice. The coordination number is used to express how many cations surround a single anion and vice versa. And this is a little bit different than the formula unit. For example, NaCl, the formula unit or ratio is 1 to 1, but the coordination number would be 6, because remember there's 6 sides to each atom. And when you think in 3 dimensions, just like a dice, and there'd be 1 chlorine on every side of the Na plus ion. So that's where that coordination number of 6 comes from. Ionic crystals contain an indefinite number of these alternating ions in this fixed ratio, so that's why the simplest ratio is referred to as the formula unit. Not just the formula, but formula unit to let you know it's ionic and the number is indefinite. So lattice energy then is a measure of the strength of attraction between the ions in the lattice, and it increases with either an increase in charge or a decrease in size, should be here. I got cut off there, let me just add that, or decrease in size of the ions. So what are some of the physical properties that arise from this lattice? Well, most of them are predicted because of this rigid crystal lattice. It means the melting point and boiling point are both going to be pretty high because there's going to be a strong attraction between the ions. That means most ionic compounds are solids at room temperature. It also means it's really expensive to melt salts and to try and remove the metal from the nonmetal using electrolysis, and that's commonly done, but that's part of what makes metals very expensive to recover. Another property is something called volatility. Volatility sounds really good, like it's explosive, but it's really just the tendency of a substance to vaporize or become a gas. So ionic compounds have very little volatility. In fact, they're often described as being non-volatile solids. And this low volatility, it accounts for the lack of odor for most ionic compounds. Because think about it, the reason you smell something is because some of the molecules escape and actually become a gas. So if that doesn't happen, it means there's not going to be much odor associated with it. Other physical properties that we often talk about are solubility, and that's how easily the solid or the solute becomes dispersed throughout a liquid, the solvent, or what we know as dissolving. So usually we're referring to the solubility in water. So the greatest factor influencing solubility is the amount of attraction between the solute particles and the solvent particles. And this is referred to as the chemical nature of the solute and solvent. But that's just a fancy word for saying, is there any attraction? And remember, the general rule is like dissolves like. So nonpolar tends to dissolve nonpolar. And that's because there's no charge separation. Whereas polar tends to dissolve polar, which means it can also dissolve ionic because they both have these charges or dipoles. So when a solute dissolves in water, we say the solute particles become hydrated. That means they get surrounded by water particles and carried away or dispersed throughout. If it's a non-water solvent, then we just say the solute is solvated, or most of us just say dissolve. But you should be aware of those other terms as well. Other physical properties are conductivity and brittleness. For any compound to conduct electricity, it has to have ions or electrons that can move and carry a charge. So ionic compounds in the solid state are not good conductors because they're held rigidly. But once you melt it, which that takes a lot of energy, so more likely dissolve it in water, it'll become a good conductor because now these ions or electrolytes can move. Ionic compounds, however, as a solid, tend to be very brittle. They do not pound out nicely like metals do. Instead, they tend to shatter, and that's because you disrupt that alternating pattern. You no longer have alternating positive and negatives, but you force a bunch of positives near each other, which causes repulsion and then the fragility or brittleness that we see. And then finally, just a word on what's called ionic character. There's a continuum of bonding from perfectly shared covalent bonds to transferring electrons in an ionic bond. And many ionic bonds are between just two elements, many of the crystal lattices or compounds, and so we call those binary compounds. And again, remember, it's going to form between those most likely to lose electrons with those most likely to gain electrons. So that means the metals in the lower left are the biggest losers and the upper right are the biggest gainers. So our most reactive or most ionic bonds are going to form between something around francium and fluorine. And you can actually use electronegativity values to predict if an ionic compound is likely between two elements because IB says it's a difference of 1.8 or more in electronegativity. Some books say 1.7, but it's around that area. So once you get to a difference in electronegativity of 1.8, the electron spends so much time with the nonmetal that it's considered to be transferred. So again, we have this bonding continuum that looks at the differences in electronegativity, which could be 0 if it's between two like atoms, all the way up to over 2, depending upon how electronegative the nonmetal is and how little electronegativity the metal has. So we rate bonds anywhere from being pure covalent to somewhat covalent to mostly covalent to being ionic. And that also then involves polarity, polar and nonpolar covalent bonds.